got me my table.
Oh yeah, you can steal your table.
No chair, just table.
Now you have all this table space to work with.
All of them are equivalent because the probability of this one
Just doesn't get used to not to taking the top without a table.
like this, they can be arranged anyway. This one can be a double bond, this one can be double bond. Like it's just.
So the residence would just be like the opposite, like A's would be the doubles, and B's would be the.
Well, it's not exactly that. It's just saying that there's like a probability of all these bonds being one. They're all equivalent because we don't know which one exactly is which. That makes this help.
I don't know what that means, like when I draw, like it says can draw relevant, any relevant.
I guess you would just draw like say this. Yeah.
Yeah.
So like you would draw like a version of this where like say this would be your double bond and so on, and you would just say residence structure. You just say that.
So like this, you can see in my erasure mark, I have these all single bonds and they were negative, and let's do that one be the residence.
Look at this fancy pens I got for you. And there's the stiff nibs, the plastic nibs.
It's okay, I love micro.
It's basically like residence structures are only when there's like say it was three single bonds.
How's that kind of a noise?
That would be residence because any of those bonds could be an egg. Like we don't.
Yeah.
Yeah.
I am so behind on
So
homework.
you just,
Say
that was
that
me
was
last
residence
week,
draw.
like I finally got caught up and was able to turn it, but with the chapter 12 homework comes.
Yeah, in different places. Yeah, like and it doesn't
I
matter.
wanna say
So,
chapter 9 and 10, maybe even
yeah, that would be.
6 and 7 too, we're both really late.
You can just flip it any way. You could have two doubles here, two singles there, just any way.
When did you find out about this?
Yes. I'll look at bottom of the fancy table.
Yeah,
Get all that space.
I'm already putting it in good
He's
use.
already running out.
Man, this
That was
jig on you.
fast colonization.
What?
Unless we're taking.
Wait, is finals next week or the week after?
Finals is next week.
Yeah, finals is next week. Last final is today, right?
Yeah.
Yeah.
What? Welcome. Oh, God.
Same.
Are we turning in anything?
I'm like,
I'm confused myself.
it really sucks
Yes.
for me because the thing that I struggle with most in history, stuff that I know, but I'll make stupid little mistakes.
Right, you gotta not have.
And then like as soon as like I get it figured out and I see my mistakes, I'm like,
I would be completely honest.
Why would I do it the correct way when I could do it the wrong? That's me.
Let's get this started.
For how long? For 2 hours. I don't even know what happened. I was supposed to watch
I think is the lab final open book?
French.
Yes, we'll have our lab.
Yeah.
Yeah.
That we teach.
The lab final. At least it was a semester.
The idea is
And honestly, like, I think that it's really practical, because when are you ever not going to have your notes in your job?
Yeah, trust me.
Like, you're always gonna have to.
No. Think about it. It's like
That's the worst thing I ever got.
those are work on
Was
it.
not the
You rest that much.
I thought that all the
So instead of filling your time with a bunch of bullshit, fill your time with those stuff all over. Makes you feel more productive and it makes you feel overwhelmed. It's not fun.
All right, let's go ahead and get started. So hopefully I passed back your papers. So I still have a few that I need to hand back out. So if I missed you, you can bug me after class, or maybe I'll try to hand some out while we do some problems. But let's look at the week, or really the end of the quarter, because we're basically almost there, which is kind of scary. It snuck up on me too. So we have our, I'm calling it a lab final, but I didn't want to cause panic, right? So it'll be weighted the same amount as all the other labs, and it'll basically be based off of, experiments we've done before, so maybe calculations, and that's why I'm trying to give all your papers back, because it's open notes, and so I would just have all your labs up, and of course you can also use the electronic labs online if you need to look through those. And then we'll also do checkout, and so that just means, and I'll have a sheet to kind of help guide us, but you'll just go through your drawer, and you can of course do this part together, so this part will be solo, and you can check out with your partner if you want. And you'll just clean your glassware, make sure everything looks good and complete based off of that list. And that's it. And that should be a free 10 points, so most people get that. So that will heavily weigh into your lab final grade as well. Yeah.
So there's going to be no lab time next week, or are we using that for exams?
So I wasn't planning on doing like lab time, but that would be a good time to do makeups.
Okay.
And so if you do need to make up anything, we can still do it either during the lab final, try to squeeze it in. So if you need to make something up, ideally come today and then final Thursday, or we can do makeups in the last week as well. So I'll put last chance finals week.
There's next Tuesday going to be like a study.
Yeah, so then next in lecture, so we won't have lab, or at least right now, mandatory lab attendance, unless you're emailing me that you're making up something, or we could do study hall, whatever, if that works for people. And so then next Tuesday, what day is that?
One of those numbers.
Some sort of single digit.
Some single digit number.
Next Tuesday
Oh, I
is
think.
the 5th.
Ah, okay. So the 5th. I was trying to open up my calendar. It's like, how did it become the 5th of December? So we will review in class, and so it'll be a similar style like I did for the midterm, so I'll kind of go over those representative problems so that you feel really ready for your exam. And then exam Thursday. And so please, if you're not going to be here this day, we need to make it up early, especially the testing center. Now you have to schedule, so it's a little bit more difficult to get that in. So that's where those lab times, if you need to do your exam early, that could be a good time as well. So just putting that out there. Oh yeah, there's a lot of homeless labs up at the front. So there's 3. One of them I've been hanging on to for a while, and I still haven't found its owner. So I think, yeah, there's a thermochemistry one, a flame test lab that I've had like for a long time that no one has, and a copper reaction. So if you're missing grades, maybe check those out. And then let me know because I need to input them, of course.
How many lab years was that? 8, 9? Do you know?
I should know, and I don't.
I think it's 9.
9.
I want to say 9, but. Or is it 8? We might only have 8.
I counted 8 lines.
Yeah, I think actually we only have 8 because we skipped. I gotta count.
Oh, that's right, because we skipped Thanksgiving.
Yeah, so our last lab was lab 8, thermochemistry. So 8 labs. And so don't forget about the journal article extra credit as well. So I think I posted the assignment. And so I'll put journal article summary.
You did post it? I just haven't started it yet.
Okay, I was making sure I posted it. Sometimes I think I post stuff. And so remember, that's 5 points bonus on our exam, on our final. And so other things, so make sure you check your grades, go onto Blackboard. And I've noticed some people have forgotten their reading questions. So get those in. So reading questions, those will hurt you for participation, right, at the end if you don't do them. So do them. Do them. They're all untimed, so 1 attempt though, but get them done. You can do it late, so a lot of you have like a whole quarter's worth of reading questions, so probably want to do that ASAP.
Object permanence is hard.
Any other announcements, questions, concerns? I'm watching the chat too. No, this Thursday, or this week, yeah. So either this Tuesday or this Thursday. So this is our last official lab time. Other questions? So I do want to put this on your radar, even though it's next quarter and coming up. But time flies, especially with the break. So next quarter, I hope everybody will continue taking this class. So that's my recommendation, is that you finish the series. And so next quarter, we're hosting a science fair. And so I need student volunteers. And so it's in collaboration with Earth Club and Alpha Zeta Phi and Engineering. And it is going to be on January 19th, so that's the second week on that Friday. And I'll probably offer up bonus points as well, so probably talking 5 points bonus, question mark, on either a midterm or a final. So again, that's next quarter, but putting that on your radar so you can think about it if you want to volunteer. And probably over the break, I'll email people or nudge people of like, what kind of experiments would you like to maybe lead and teach, and we can talk about this. So this should be really fun. So yeah, just let me know if you're interested in it. You don't have to be in any of the clubs, although I'm sure all the clubs would like it if you join. We do have Earth Club people and engineering people, so woo. All right, any other announcements or things I should talk about? Other than thermochemistry, I mean. All right, so let's get into thermochemistry. So I know, so this is right, the problem of the college-paced courses. So yes, we're still learning new material and you will be tested over it. So let's get into it. So what is thermochemistry? And so it's just defined as the branch of thermodynamics that deals with heat. So usually either evolving heat or absorbing heat in our chemical processes. So describing reactions as endothermic, exothermic. So we'll be learning those terms. And so what is energy? Oh, are you trying to take a picture or something? So energy is defined as the capacity to do work. And so we'll have to define work in a second. And energy is either potential energy, and usually for our purposes, we care about what's stored in the chemical bonds. Of course, right, you have gravitational potential energy as well, but we won't talk about that too much in this class. And then, of course, we have kinetic energy. So we can think about this as energy associated with motion, but we'll also relate it like to molecules and temperature, right? So increasing temperature, increasing kinetic energy. And so let's define work. And so work is path dependent. So we should put that, so path dependent for work. And this is defined as the force acting over a distance. And so that's where, again, the path dependence comes into, is what distance are you actually doing the work over? And again, so work is just force times distance. Again, this is a general definition for our purposes. And so now let's look at the first law of conservation of energy. And so our first law of thermodynamics states, so it's conservation of energy, so that means that our total amount of energy in the universe is constant. So, right, it is conserved, so energy is just converted from one form to the other. And of course, right, we can never design a system that would continue to produce energy without some sort of energy source. So do you guys know what this is referring to? There's like a theory. What are those machines called?
Nuclear? Or, oh, you're talking about
Like
the
a
perpetual motion.
Yeah,
machines.
perpetual motion machine. So that's what it's referring to, right? So we can't, AKA no perpetual motion machine. Yeah, that's related. So nothing can have, and this is kind of cool too. So we could talk about a few things, a few theories if you wanted to think about stuff. So yeah, we mentioned perpetual motion, so that's just, could you somehow come up with a machine that powers itself? But obviously that violates the first law of thermodynamics. And of course, right, people did try to make some device, or obviously that would be cool in theory. The other thing, if you get bored and want to think about, I don't know, the universe. Yeah, so this is some topic. Again, it's another theory, and so it kind of goes back to, well, we can't have 100% efficiency, and most of that is lost to heat. And so obviously, right, we're nowhere near here, but basically, could we ever reach a point where we can no longer perform work and all our energy is lost to either entropy and heat? And so, right, there's this whole theory on how the universe will just go to a point where we can't perform any work, so everything would just be in thermodynamic equilibrium, and yeah, it would be heat death. Who knows? It's something to think about, but then you have to get into, right, the Big Bang, and is our universe expanding? Is it going to contract later? Yada, yada, yada. But this is something to kind of think about. Like I said, if you get bored, I want to think about things like that. All right, so back to the systems and surroundings that we can look at and understand. And so we can think about our calorimeter experiment. And so we have the system as just defined as the part of the universe that is being studied. So for our case, right, that would be our little calorimeter and the little reaction that we did, so dissolving magnesium or dissolving magnesium oxide. So we were studying, right, our system. And then so we can lose or gain energy from our surroundings. And so our surroundings is everything else then, and everything else in the universe that can, of course, again, exchange energy with our system. And so, right, we were trying to, of course, limit exposure to our surroundings with our experiment, right? We had our calorimeter, our little styrofoam, that was supposed to be providing insulation, so we're just measuring, right, the heat of our reaction, and we're not losing it to the surroundings. And that's also why we had to figure out our calorimeter constant. So I'll put, right, calorimeter constant, so, right, how much heat were we losing because of our calorimeter, right? Because we obviously didn't have a perfect calorimeter, so we were losing to the surrounding. And so you've gotten a small taste of this in lab. And so again, thermodynamics is just the study of the energy exchange between the system and the surroundings. And we can have scenarios where energy can flow from the system to the surroundings. And so maybe you've experienced an exothermic reaction, right? And it gets hot. What exothermic reactions have we seen in lab, or maybe not even in lab, but what you're aware of?
Hydrogen plus fire.
Hydrogen plus fire. So yeah, that's extremely exothermic. That's a good one. So burning, so we really like burning in this class. So of course combustion.
What was the plastic bag one? I don't remember what we were mixing, but it got warm.
Oh,
Do you
was it
remember?
the,
I don't remember
yeah,
what
the calcium chloride,
Yeah.
and then you mix other things with it.
And you put it all in the bag and mush it up.
Yeah,
That doesn't involve combustion.
the other example, so I was thinking of a couple examples. So if you dissolve, so sodium hydroxide or other bases in water, that's extremely exothermic. Or, you know, those little like fire hand warmers.
Yeah, you pop the little metal disc in them.
Yeah.
And then, like, the liquid in it all gets
Yeah, it depends.
hardened.
Because I was thinking, because I think some of them have just like iron metal even, and they're exposed to oxygen and gets warm. And then, yeah, there would be other ones. So it depends too. So you could have, so now let's talk about endothermic reactions. And watching the chat, so decomposition of carbon dioxide, that'd probably be combustion. And then, so an endothermic reaction, so energy flowing into the system. I think if you dissolve ammonium chloride or something, that tends to be endothermic, and so it takes heat, so that's in like those little ice packs, like those instant packs. Or they also use like urea or some sort of crystal and water, that's also endothermic. Other endothermic reactions, or you can always exothermic.
Is it either fission or fusion one of the endothermic reactions? Is it?
Yeah, that's what I would assume. And, oh, I see in the chat photosynthesis, so that would be endothermic. That's a good one. Photosynthesis.
So then would it be accurate to say that in broader metabolism. Catabolism would be exothermic reactions, and anabolism would be endothermic reactions.
I don't know those terms. Catabolism, sorry.
Oh, catabolism is basically in your metabolism, you're taking like sugar molecules and breaking them apart into simpler and simpler sugars in order to like get energy to fuel your body.
Yeah, so
And
then,
anabolism is taking these little building blocks of nucleic acids, putting them together until you get DNA.
yeah, so that's basically it. We just have different terms. And that, we'll circle back to that idea, because
Okay.
it is relevant, yeah.
So in the ice pack, because it's endothermic, is a part of it heating up because energy is going into it?
Well, your body's heating it up. So that's why it feels cold to you, right, with the icy pack. So you crack that salt, and then the salt takes your body heat to dissolve it, and then it feels cold to you.
So I was right, that fusion reactors are like an endothermic process.
Oh,
Fission is
Because fusion is putting two atoms together. Is that right?
yeah.
It's endothermic up to a certain point.
Yeah, the thing is that it's also, um,
The whole thing is we're trying to make it exothermic so that
Yeah.
it works as an energy
Um,
production system.
how it works is you're shooting particles at atoms to make them unstable, and then they break apart, right, essentially.
Yeah.
But you get them close enough to where you can get a really strong interaction.
Yeah, so I guess with fusion, right, you're trying to, well, at least what they've, so are y'all familiar with like what they've done with the fusion reactors?
They got it to where they finally have like a positive, like a net gain of energy.
Yeah.
It lasted like a tiny bit,
Yeah.
though, right?
But then, so y'all heard what they did though, right? Because they basically concentrated a bunch of lasers though to like one tiny little part, and it was also like really crazy because didn't they have hydrogen and like some tiny little metal bead, if I remember correctly? Because they had to like hit it right and then like vaporize it in such the right way that it, made a new heavier atom. And I'm not even sure what it made. I would have to look it up, but.
Now a lot of the time they make helium. May have not been the case with that one.
Yeah, I'm assuming it's either helium or tritium or something.
Yeah.
Isn't placing something in liquid nitrogen like an endothermic reaction, right?
Well, if you're just placing it, then you're cooling it down.
So no.
Well, it wouldn't be like a reaction, but if
So
you're,
like an ice cube melting isn't really a reaction.
yeah, it's a state change, but it's still, it would either be exothermic or endothermic. So if it's cooling down, well, it depends which way you're looking at it, right? Because the liquid nitrogen is transferring heat, or the other way around, right? Your object is losing heat to the liquid nitrogen, trying to cool it, right, so to reach an equilibrium point. But yeah, still endothermic, still exothermic, but just not reactions. And then there was a question is if you reverse a reaction, will it be like exothermic or endothermic? So yes, you can reverse it, right? And the signs change, assuming the reaction does indeed go in that direction. And so let's look at some work done. And so we're going to examine a piston and kind of define work here. So we have a system enclosed with a cylinder and a piston, and so our force is applied to the piston, so in this case, right force pushing it down, and so it causes displacement. So we have our volume change. So any sort of piston action is either work being done on the system, and so we have this pressure is, of course, force over area. And so that means pressure volume work is work caused by a volume change against an external pressure. And so when a gas expands, our change in volume is positive, but then we have to think about, right, how it's expanding. And so you can think about, a balloon. right? And we have to think about all the molecules inside. And so, of course, right, we have the pressure of air kind of beating down on our balloon, right? So in order to expand, our molecules inside have to work against, right, this pressure. And so our system is doing work on these surroundings. So our gas is negative, so our gas is performing work. And this is at constant external pressure for our purposes. And then we
the
can,
lowercase w is work, or is
yeah,
that just gas?
this is work, but we are looking at work performed by the gas, right, due to a volume change. So this is just, yeah, it is work, right, but then we're only looking at a specific instance of work. And so then it's defined by this formula. So negative pressure times our change in volume. And so we want to be in joules. And so we can use this conversion then that 101.3 joules is equal to this unit of ATM liters. So watch that, right? So that means we're going to be plugging in work first. So our pressure needs to be in ATM. Volume will be in liters for this formula. And then we'll just multiply by this number, right, to get it back in joules. So let's try that. So it says to inflate a balloon, we have to do some pressure volume work on the surroundings. So if you inflate a balloon from a volume of 0.1 liters to 1.85 liters against an external pressure of 1 ATM, so regular atmosphere, how much work is done in joules? Then chat, you can post answers too once you have them. So do we have answers for this one? Still punching.
I got negative 86.105.
So negative
Or it's doing 86.105.
oh, 86. 86.5 you said?
0.105.
0.105. So I'll just punch that in and double check. Is that what people got? Let me pull up my calculator just so we can all go through it. So we can find our change in volume, so 1.85. minus 0.1, and it was already in liters, so that's good.
Oh, wait, no, I did that wrong then. For some reason, I thought that was 1 liters, so yeah, mine.
Oh, so we might have a typo.
If we're going from 0.1 liters to 1.85 liters, wouldn't it be 0.1 minus 1.85?
Final minus initial though,
Oh, okay.
because you're also looking at, so if you get confused with the sign there, right, you can just look at, is the balloon inflating, right, because that's the key, because basically if the volume is increasing, the work done by the gas has to be negative, right? And then the other way, so if volume decreases and your balloon is shrinking, your work gas is positive. So that should help you, but the signs should work out. So yeah, it should be final minus initial, and then so multiplied times our pressure, so 1, and then convert it to joules, so times 101.3.
Actually, should be 177. Yep, okay.
So did we get 177 then?
Yes.
So I'll just work. So 1 ATM 1.85 minus 0.1. Sorry, just writing that out. And again, make sure it's negative. I'll just round it 0.3 joules. All right, questions about this problem? All right, so this is a good kind of cheat sheet. So now we have our sign conventions. And so, right, we're looking at kind of 2 major things right now. And so we have our Q, that's just defined as heat. And so if we have a positive sign, then we're saying that it's gaining energy, like an endothermic reaction. And then if Q is negative, right, then it's losing energy, like exothermic. And then work, so we said work done on the system. So again, if you want to make a note, volume's decreasing, so work's being done on it. And then we saw a negative sign when work is done by the system. And you, again, might want to put volume increasing. And then we'll look at our total change in internal energy. So again, energy flowing into the system, so looking at Q plus W, and so overall energy flowing into the system or energy flowing out. And so we often use these different energy diagrams to show these exothermic and endothermic processes. And so we have our energy flow. And so for exothermic, we can see our products are lower in energy, right? Because we've lost that energy as heat. So we can say, right, delta energy, lost as heat. And so all we're saying is this reaction is, again, exothermic. So carbon plus oxygen gives us CO2. And so where does that energy go? So if it's flowing right out of the system, then of course it has to go to the surroundings. And of course, right, we feel that exothermic, so it's going to be hot to us. So we're getting heat versus the system. And of course, these are always equal in energy because, right, first law of thermodynamics, we're not losing or gaining any energy. And so this helps with the chat question. So, right, we can reverse it, flip the process, And yes, the flip process would be endothermic, ideally. And so now we have CO2 decomposing to carbon and oxygen, and these products are higher in energy. And so again, we just have energy on this side, showing that we put energy in. So again, endothermic, how much heat we gained. Again, we'll feel cold, right? Because if we're touching it, we're supplying the heat, so we're making this reaction go.
So then you would be part of the surrounding?
Yeah, exactly right. So you're part of the surroundings, exactly right. You have your closed system of this reaction, and we feel we're losing energy, right? We're getting colder as that energy goes into the system. And so this means that energy can be exchanged between the system and the surroundings through heat and work. So we're kind of, again, seeing that. And like we said Q is just heat, so endoexothermic, and then W is the work-related energy. Again, usually with our gas expansions or contractions is how we'll look at those. And so important to at least note, right? And so I had mentioned, so work was path dependent, and so Q, same thing. So both of them are not state functions, right? Their values depend on the process. And so again, right, we can see that. So obviously some sort of exchange. So depending on what's going on, right, are we expanding? Are we contracting our balloon? Or is it exothermic, endothermic? So all that gives us to our total energy. And so now this brings us to more detail on how we're actually going to measure it. So we're going to look at enthalpy. And so enthalpy is just defined as heat evolved at a constant pressure. And so again, right, those are the conditions that we're mainly interested in chemistry, is just things happening at our constant pressure, at least for our purposes right now. And so enthalpy is the sum of the internal energy of the system and work. So this is, right, just Q and work right here, essentially. So Q plus W, so that's all that's being shown here. And so like we saw in lab, the key point, and we can kind of star this, is that enthalpy is a state function. So, right, it was not path dependent, so that's why in lab we could do those other reactions to give us the overall reaction we were looking for. And so we see, right, at a constant pressure, oftentimes the enthalpy is just the same thing as Q. So that's the distinction. And so again, usually our enthalpy and our total delta E are pretty similar in value. And so the only difference would arise is if you have reactions that produce or use large quantities of gas. So then that's where the difference of pressures starts to come into play.
Can you explain what a state function is? Like, what it's defined as?
So a state function just means, right, that it's not path dependent.
Okay.
So not.
And the path being the reaction?
Yeah, so the path has to do, the better analogy is like, right, taking a hike, or whether you go kind of straight up and take the harder route or do a long loop. But yeah, with the reactions, it kind of depends on your system and what's going on. But for our purposes, right, we're not going to be looking at weird changing of gases. That And so now let's look at Hess's law. And again, we kind of saw this in practice without knowing what we were doing. And so, right, enthalpy of a reaction is always associated with a particular reaction. And so if we reverse it or double it, then our change in enthalpy also reflects those changes. So it's an extensive physical property. And so usually, right, it's given in some molar amount, or in this case, right, so this one is telling us, so we have one equivalent of carbon plus one equivalent of oxygen gives us CO2. And so this is going to be, right, negative 393.5 kilojoules. But then we can multiply it, so multiply everything by a factor of 2. And so now that we can double our enthalpy, so again, that's why it's extensive.
Can you scroll up just a little bit?
Let people, yeah, question.
Enthalpy is just change in heat.
Yeah, so that's what it ends up, that's what it ends up being, right? Because it's technically this, so it's change in heat plus that work, but we usually just end up looking at the change in heat, right? Because we're not looking at like volumes and gases expanding in our cases, yeah.
So basically it's change in energy, but usually we end up looking at the heat aspect of it more.
Yeah,
Okay.
yeah, that's exactly. So we've kind of oversimplified it for chemistry. So like maybe for physics, if you take a more detailed look at the different like processes, you would go more into detail. But yeah, for our purposes, it's just kind of looking at the heat of exothermic, endothermic. And so like we saw in lab with our little examples, so we can reverse the reaction. So we totally flip this. So products came reactants, reactants products, and then that flipped the sign. So it was negative, became positive there. And so there's a couple of different ways to do this. So we can calculate our standard enthalpy change for a reaction from, let's start with this method here. And so, right, any reaction can, of course, be written as a sum of formation reactions for the reactants and products. Oh, what the heck does this mean? So our delta H of the reaction, then, is just the sum of our delta heat of formation, which is just a standard for every element for our component reactions. And so we'll go all through this, but all it's saying is, right, we'll sum up our products, and you can see, right, it's just generally products minus reactants. But because it's extensive, right, because it depends on the amount, they have the little n here, which says we're going to multiply it, right, by how many there are in the reaction. And then you sum up all your products. This just comes from a data table, and then you sum up all your reactants and then subtract that. But like I said, we'll do an example.
And we kind of know this because each molecule has the same amount of bonds with the same amount of energy in those bonds, and we know how, like, taking them apart, how much energy is released, so we can assign a value to it.
Yeah.
And just math it out.
Essentially, someone has done, right, yeah, our standard heat of formation, or they've done the calculations. And so let's look at when we can use it. And so, right, we have our standard state, and again, for our purposes, we'll mainly be in the standard state. And so pure gas is at 1 atm, and then pure solids or liquids are usually in their most stable form, right, at 1 atm, so their usual state of matter. So, you know, water is a liquid, that sort of thing. And then our standard concentration is 1 molarity. And then, of course, our standard enthalpy change, this delta H with our little dot here, is just our enthalpy change when reactants and products are in their standard states. And so this is kind of helpful, but you'll see that you don't really need to know this because your chart will remind you. And so now we'll just look at, right, our standard heat of formations for different substances. And so all elements must be in their standard states. And so the delta HF for a pure element in its standard state is 0 kilojoules per mole. And so let's just look at a couple of examples. Oh, sorry. Good. Give me a second to copy that.
What's the last bit about the substance in a solution of concentration 1 mole? Is that just what a pure solution or something?
Yeah, if you're just doing like a solution of anything, you know, hydrochloric acid or any.
You just usually assume it's at the concentration of 1 mole?
Yeah, or that would be the standard condition.
Okay,
Yeah. Should we scroll down to the table or?
Scroll up a little bit. There we go. I missed the last bit about the little.
This one?
Yeah.
Okay, I'll let people copy that. Okay. Are we good on this part down here? Got everything? And so if we look at the chart, so we'll just kind of orient ourselves with this chart. And so we can look up all our different elements. And so, right, all our substances that we're interested in, we would look up on any reaction that we're doing. So this is not a complete list. I just kind of pulled up another one, you know, randomly. So again, you can just kind of appreciate it. Notice the units, so they tend to be in kilojoules per mole, so they're both the same. But just always watch your units and make sure that the chart is indeed the same. It could be different. And so we can also take a look. So it said that pure elements in their standard states were 0. And so we can look at that. So bromine is a liquid at room temperature. So that's why it's 0. And then we can see, well, in the gas state, that took energy to get it there. So it has 111.9 for the gas state. So that's kind of interesting, or, you know, again, appreciate that. So notice carbon, so graphite is set at 0. And then diamond is a little bit higher heat of formation. Again, appreciate it, right? So the form does matter.
It needs higher pressure?
Probably, yeah, so it does need higher pressure. I also know that just the graphite is more thermodynamically favorable. So, yeah, it probably just has to do with the structure, even though the diamond is pretty, I mean, it's pretty strong, obviously, because it has a tetrahedral, but I'm not entirely sure why, but just the thermodynamics is that the graphite is more favorable. But. And so we can look at other compounds. So, you know, just methanol, we're looking at one, liquid state, negative heat of formation. So just appreciate all of them. So let's see if we can put this into practice then. And so it says use the standard enthalpies of formation to determine the delta H of our reactions, or change in enthalpy for this reaction. And so let's see, how should we do this? Let's find the values that we need.
Is there a chart like that in the chapter of the textbook that you use?
I think it's in the back of your book, but it should be there. It should be a reference chart. I'm trying to pull up your book as well. So let's see, let's find all these. So let's start with ammonia. I'll write them above. So ammonia, and check your states, right, when you do this. So ammonia gas state, so negative 45.9, and again, that's all going to be kilojoules per mole. Oxygen, this should be 0, right? It's in its standard state, but we could check. So oxygen, gas, 0, okay. That's what we expected. NO, let's see if we can find NO. NO, so gas state 91.3, and that matches. And water, gas state, so again, pay attention to the states. So your gas state is negative 241.8. And this came up in your lab, remember? Where it mentioned this difference in energy of the liquid to the gas state. And again, appreciate that the gas state is slightly more positive, since, right, energy had to go in to make it a gas versus our liquid state. So our gas is negative 241.8. All right. So given those numbers, see if you can figure out our delta H of our reaction. Let me know if you have answers. So watching the chat for answers. Looks like people are still punching in. They were all in kilojoules per mole.
Well, then I think what happened is that this reaction takes an extra 902 kilojoules of energy, so it's endothermic, and it takes 902 kilojoules of heat from the surroundings, I think.
So let's,
I got the same value, but I think it would be exothermic if it's negative, right?
yeah, if it's negative, it would be exothermic. I haven't done it, so let's walk through it. So products minus reactants, and of course you have to multiply by 6, so negative 241.8, oh my gosh, times 6, and then plus our other products, so 4 times this 91.3. So is that what you got for the product side?
Yeah.
So negative 1085. And so we need to subtract our reactants, but let's figure out what our reactants came out to. So 4 times negative 45.9. And so now it should be negative 1085.6 minus a negative answer, so adding. And so, yep, got your 902.
I think I just didn't realize that the negative meant that it is doing work on the surroundings.
Well, then it's exothermic, yeah,
It's exothermic.
since we're not talking about gas expansion. So yeah, no work in this problem, right? Because there's no gas expansion, it's just, we're only looking at heat right now. Excellent, so did we all get negative 902? And that would have been kilojoules. So just watch the signs.
Kilojoules per mole?
Well, now it's no longer per mole, right? Because we multiplied it by the appropriate coefficients to just leave us with kilojoules.
Okay.
Any other questions on this one? And I'm sure your value could vary if you used other charts. I'm just kind of glancing around what this one says. Oh, no, I can't even find water on here for reference, but, oh, there it is. It has the same value. I'm just always curious. You might find discrepancies, but. And so we probably know this instinctively. So everybody was talking about explosions and chemical reactions, right? So the more reactants we use, the larger the enthalpy change, right? So the larger the explosion or the boom or the more heat that it's absorbing. And so this means that we can also, of course, calculate our enthalpy change or our amount of moles. Oops, we lost our arrow sign here. And so this reaction, so when we're looking at these, we always want to look at our reaction. How many moles is this written for, right? What's our delta H? And so, right, this is telling us that 1 mole of propane, that the combustion of it produces negative 2,044 kilojoules. We can also reframe it in the terms of oxygen, right? So we burn 5 moles of oxygen, and that was equivalent to negative 2,044 kilojoules. And so now let's see if we can take this to the next step. So we have this information. They reworded it or repasted it down there, but can we figure this out? So we have a propane tank in the home. Barbecue has 13.2 kilograms of propane. So note the kilogram. And so calculate the heat in kilojoules associated with the complete combustion of all the propane in the tank. not sure you need the table. How are our calculations coming?
I have an answer. I started just by converting the 13.2 kilograms to grams. So multiply it by 1,000, you get 13,200 grams. And then I found the molecular mass of propane, which was 44.097 grams per mole. And then I divided 13,200 grams by the molecular mass to get the number of moles in that amount of propane.
Do you have a
It was right about 299 moles.
299
Close.
of propane? Excellent.
Then I just multiplied that by the negative 2,044 kilojoules per mole.
That sounds excellent. So key step was, of course, getting to here, right, saying that we have to go kilograms, grams to moles, and then, yes, we can relate it back, just like Andrew said. And so what do we get for a final number? I can barely read, so negative 611,000 kilojoules. It's a lot of burgers. Let's see, oh,
If you want to round, you can do 612.
oh, thanks.
Yeah,
Yeah, I was trying to do 3 sig figs. Kilojoules. Excellent. Questions about that one? Questions?
I am unsure about the relation, like how you jump from moles to kilojoules.
just multiply together. It's like 1 mole of that propane equals that 2,000, negative 2,044 kilojoules.
Oh, okay,
So if
okay,
you've got
okay.
299 moles, multiply that by that kilojoules per 1 mole.
So does that make sense?
Translate.
So 1 mole of the propane gives you negative 2,044 kilojoules.
Yeah.
So then if you have, then you would just multiply that by however many moles of propane you have?
Yeah.
Okay.
Yeah.
Now it makes sense.
And we could have figured out, right, our delta H of the reaction. If they didn't give it to us, we could have gone back, right, to our standard heat of formations, figured out the reaction for kind of 1 mole written out, and then scaled it up to however many moles, or scaled down if we were doing a small scale. But, and I couldn't resist a Hank Hill picture for the propane. Gotta love propane. All right, so now we'll take a small look at, well, what happens if pressure is not constant, but we probably won't do too much of this, like I said, but we should at least be aware of it. And so just restating what we said before, right? So we said enthalpy was really the sum of the internal energy and our work. And so I like rewriting it as Q plus W. That kind of helps me. Okay, heat plus our work aspect. And again, re-highlights if you need to that our enthalpy is a state function, aka not path dependent. And so we basically said, well, for our purposes, we're mainly looking at this, where our enthalpy is related to Q. And remember, Q is just heat, so if you need to write that heat, do so. So there's a lot of variables in kind of thermodynamics. And so usually, like we've been looking at, they're very similar in value, and it's only when we have these reactions that produce or use large quantities of gas. And so how do we calculate it? So what if our pressure is not constant? How would we calculate our internal energy? And so how we would do it is, so then we have to figure out our change in volume of gas. And so we would look at, so it says we take the sum of the stoichiometric coefficients of gaseous products. So anything that has a G, right, add up all those coefficients. And then minus, so you're basically figuring out how does your moles of gas change, right? Is it growing? Is it becoming fewer? And then you subtract it from the sum of the coefficients from the reactants. So, right, products minus reactants, again, summing up all the coefficients. So that gives you your change in volume. And so now this pressure times change in volume is equal to our change in volume here times RT. And so this is related to our gas laws, right? So PV equals nRT. And so now we've taken our pressure volume and stuck RT into there instead so we can solve for it at our different volumes. And R in this case is 8.3145, and that's joules per mole Kelvin here. So let's look at this. And so we can work through it. So we can figure out, right, at least just our difference then from our change in gaseous reactions. And so how many moles of gas do we have on our reactant side? So we have 3 moles of gas. So, right, just adding up our coefficients. And then how many on our product side?
Well, gas would
2.
be 0.
Yeah, so watch those state changes. So, yes, 0.
And we only care if it's gas because gas is the only state that can be pressurized.
Right, so right, because, yeah, gas is going to be expanding, so all the liquids, all that doesn't matter.
Sorry, I may have missed this. What is the R value there?
Oh, R is here. So this is just a gas constant.
Oh, just the constant, okay. Including that T part, or is that something?
And then T would be temperature. Yeah, since it's per mole.
What does the
Kelvin.
constant mean? Just the rate at which it condenses?
Well, so the gas constant is it's really related to the unit, but there's a lot of different gas constants, depending on what you're calculating. But this is the one more associated with work since we have joules and moles Kelvin. But you'll see, if we go to other chapters, we'll look at other gas constants because they're based on other units. Yeah, this is kind of an aside. but we could still look at it. So if you just Google gas constant, for example, you would get a bajillion things because this all just depends what you're plugging it into. So in our case, we're looking at joules and Kelvin and moles, so that's why we're on this R. But you can, again, for right now, just appreciate that there's a gas constant for a bunch of other units. So I'm not sure if that quite answered your question, but. All right, so then we're trying to figure out, again, our internal energy change. So we have our delta H of our reaction. So now let's plug these values in. And so I'm realizing we didn't get a temperature, but let's just assume it's probably right, 298 degrees Kelvin. So that's about our room temperature. And so we said products minus reactants, so 0 minus 3. So we have, right, our delta V gas is -3. And so now we can figure out our change in internal energy. And so let's do that. So we can just plug in our values. So -3 times our appropriate gas constant for this scenario. And so joules per mole. And so there's our molar amount. And then Kelvin. So again, just assuming 298 since I failed to give it to you. And,
The units on that R, that constant, it's joules per mole.
yeah, so joules per mole Kelvin. And so, right, you.
Kelvin, or is mole Kelvin a different thing?
Oh, it's moles times Kelvin, yeah. So yeah, moles. Yeah, so moles cancels out with our 3 here. Kelvin cancels out with our temperature, leaving us with joules for our unit. And then if we plug it all in together, so 3 times 8.31, oh, sorry, times 298. And so this is joules, so about -7.4 kilojoules. And so, right, we can say that our delta heat of reaction and our internal energy differ then by this amount. And so we could then figure out, right, our total internal energy. So U of our reaction is given, right, by our delta heat of the reaction minus our P delta V. So, right, that was just Q plus work essentially. So just re-simplifying. And so if we look at this, so now let's get our true value. So we were given our delta heat of the reaction, so -571.6. And then minus a negative, so plus 7.4.
Because the pressure is 1, we're assuming pure gases.
Yeah, well, volume would decrease too, so that's where we end up with a positive work overall. So then -571.6 plus 7.4, and so that gives us -564 for the value.
And that's specifically the heat.
Yeah, so this is like the true energy, so yeah.
Because you lose some energy in that pressure or the change in volume.
Exactly. But kind of the point that's made in the textbook is that these values are pretty similar. So, right, we could do the percentage, so kind of figure out a percent error, right? So minus this value. So divide it by what we got. So times 100 to put it as a percent. And so it's a 1.3% error, right? So not too significant, but, you know, you're aware of it.
What is the U?
So that's just our total energy here. Yeah, total internal energy. So,
Okay.
and so that's our heat of our reaction, Q plus our work.
Thankfully, they seem to use that same U sign in physics for internal energy.
Yeah, so sometimes this is just E as in, so this is just like total energy. But you can see different, they change symbols all the time.
Yeah.
I don't even know why.
They used an H up there.
Yeah. All right, so let's,
But basically the energy lost in the volume is pretty minimal most of the time.
yeah. So, I mean, it depends what conclusion you want to take away from this. You can either take away like, oh, that's why most of the time, right, we don't even care. And that's where it makes that caveat of large quantities. So, you know, once you get on maybe the industrial scale, or if you really have, you know, a large difference in molar quantities, then it might become more significant. But you're kind of seeing how, for our purposes, it doesn't really even matter too much. So probably most of the time they ignore it in the problems. All right, so now let's look at our Hess's law, which was basically our lab. And so, right, we said, so if a reaction can be expressed as a series of steps, so that's what we did right in lab. We took our overall heat of formation reaction that we wanted, burning the magnesium, but then we said, well, we can't do that one, or at least not as controlled and easy. And so that's why we broke it down into those steps. And then we try to figure out how you can sum those different steps, right, to give you your overall reaction. And like you saw in lab, again, it doesn't matter how you get there for enthalpy, it just does it equal. And so this just gives this little scenario here. So if we care about C to D, well, we can add the process of A plus 2B gives us C, and then add this as well of going from A plus 2B to 2D. So adding those two processes together to give us our overall delta H. All right, so let's try a practice problem. And so we want this reaction. So our standard heat of formation of propane, so adding these in their elemental form. And so see if you can add these to give us this reaction. And remember, you can multiply it too by different amounts. So let's at least hear some ideas. So how can we at least manipulate these equations to get us to the top one? And it could even be, what's a good first step? Yeah.
We could double the entropy of the H2O reaction and subtract that from the propane. Right?
So we usually want to add,
I was thinking we want.
but I like doubling. So yeah, times
Yeah,
2.
we want 2 of the H2O reaction, and we want 3 of the CO2 reaction.
Okay, I like that. And so we said 3 of the CO2. Trying to just keep track of what we did. Oops. Okay. Then what else do we need to do? Because we still need to get, I like where this is going, but we need to get right propane. So right now it's a reactant. We need to get it to the product and maybe start, yeah.
So like on that top reaction, if we switch the direction of the arrow, then it's a reactant, and then we have the 3CO2 and the 4H2O from the other equations, right? So if we like add those two equations together, we're getting on the other end now the propane and the 502, and we have 502 on both sides, so we can take the 502 out.
All right, so did I think I forgot to double something. Yeah, I forgot to double this O2, but y'all are on the ball. So you said 5 oxygens, so that was product, that's good. You said the waters cancel, that's correct. The CO2s cancel. So that looks good. And then so that leaves us with what we want. So we said 4H2, 3 carbons, everything else is gone to leave us with our propane. Good. And so don't forget to flip this. I almost forgot to write it down. And so now I think we're ready to add. And y'all can help me as well, make sure I don't do calculator typos. Times 2. Oops, oh my gosh. All right, I got this answer. So negative 104.7 kilojoules. I see nods.
Yes.
Okay, sounds like everybody's on that page. So negative 104.7 kilojoules. Oh, I don't know why I wrote K twice. Excellent. Questions on that one? Y'all did pretty well on that problem. Yeah, we were flying through this chapter. Blah, blah, blah. Okay. And so this is, again, repeating our kind of standard enthalpy formation so we don't forget. And so now we have, well, what is the standard enthalpy of formation? So what does it mean? And so we saw the values, right? So first we just said, well, it means this, and we had our chart. But now we're going to really define, well, what are we measuring? And so let's look at the definition. So it's the enthalpy change for the reaction forming 1 mole of pure compound from its constituent elements. And so this is weird language, and it's also kind of weird because it's not chemically intuitive, is how I call it. It's like, what happens if we could just literally take all the elements and then combine them? And so what I mean by that is, so let's start, let's just write one for, iron chloride, for instance. So it's literally saying So we look at its constituent elements, what elements it's made out of. So it's made out of iron and chlorine. So what happens if you take iron, and of course it would have to be in its solid state because it's a solid, right, at room temperature, plus our chlorine, which should be a gas, and then what is that? So that is literally, right, what you're really calculating. Oh, sorry, too fast. And so in this case, right, sometimes we use the half equivalent. So I think this was from lab where it said like find the standard enthalpy of formation of CO. And so that case, right, it's carbon plus half an equivalent of oxygen gave you CO. So kind of strange. And so see if you can write it then for our magnesium carbonate and this organic structure here. So I'll give people a few minutes. We can tackle this magnesium carbonate one first, and then just double check that we're all on the same page. And so what do we get for magnesium carbonate?
Magnesium plus carbon plus 1/2 O2. Or 1.5.
Yeah, I just wrote it, it's 3/2. So magnesium plus carbon plus 1.5 oxygen gives us magnesium carbonate.
So you don't want to be, fractions on the coefficients are basically okay.
Yeah.
Okay.
So it'd be okay to do like a 1/2 O6.
What'd you say? Like
1/2
that?
well, a 1/2 coefficient and then O6 or that doesn't.
Oh, you're talking about this one? Oh, you just
Well,
need
I think
3.
I wrote the oxygen incorrectly. You did it with 3/2 and then O2.
Yeah, that's fine.
Get it to 3.
Yeah, 3/2 times O2, so that's fine. Either way, right? 3/2 or 1 and 1/2.
Yeah.
Whatever. But yeah, you'll have a weird coefficient for your diatomics normally. Excellent. So try that now for the second one here. I'm actually not sure what. Yeah, I was thinking it's probably a sugar. I think you're right about it being glucose. Do we have an answer for this one?
Yep, I got 6C plus 6H2 plus 3O2, and then that arrow and glucose C6H12O6.
Excellent. So that looks good, and you should put all
Oh, yeah,
the states. Yeah, and again, they would just be at their standard states. So carbon's a solid, hydrogen's a gas, oxygen's a gas, and then glucose should be a solid sugar. Excellent. All right, so that's just the definition. So anytime you see, write the standard enthalpy of formation, this is what they're looking for. And then, of course, the next step is maybe adding a series of equations, right, to get the overall change in enthalpy. All right, so let's keep marching on with this chapter. And so now we get to bond energies, so we can go back to what we were saying of biology. So, sorry, question.
So if we were wanting to make the glucose, now that we have the things that we need to put in, would we just heat this all up?
Well, so that's kind of the problem with these reactions. So this is just giving us like the math behind it, the theory, right? But the problem with this and why it bothers me as a chemist is because you can't actually do that, right? You can't actually stick in 6 equivalents of carbon plus hydrogen plus oxygen, and it's not going to give us glucose in that chemical sense. So that's why, going back to the lab, I think that's kind of the best example. It's like, yes, we wrote out what we wanted, right? So we wanted to figure out the combustion reaction for our magnesium. But then we can add, right, our series of equations. So obviously this doesn't happen, but then we'd have to look into like, well, what equations do add up to give us this process?
So we're figuring out like the theoretical
Yeah.
behind it, but if you just throw carbon, hydrogen, and oxygen together, it won't make sugar.
Yeah.
It would make like a billion things if you did.
It would just be horrible. I mean, probably just the water and the hydrogen and oxygen would just react first to make a bunch of water and explosion, and then the carbon would look at you. So, but yeah, that's what they're bothersome to me chemically, because yeah, they don't make sense chemically. It's just kind of the theory, the math behind it, and unfortunately, we can't just mix everything.
So is there a way to know what it would make, or is it just test and find out?
Sorry, I didn't hear you.
Is there a way to know what it would make and like how
Oh wait, like these horrible things would make?
if you did want to make glucose, like how
Then you have to look for like other known equations if you're like measuring it, right? So then you'd have to look at.
If you want to make glucose, you just go through the entire process of photosynthesis.
So I mean that's like right another way to break it down. So glucose is probably a difficult example because it's involved in a lot of other reactions, but if you had like the combustion of glucose, right, that would give you at least some breakdown of CO2 and water. We'd have to make a better problem. Well, in this case, we just weren't given like enough equations to do it, but yeah, like brute force could be involved. But. All right, we'll at least start bond energy. And so bond energies, so of course, right, chemical reactions either involve breaking bonds or making bonds. And so then our delta H of our reaction can also be estimated by comparing the cost of breaking old bonds to the income of making new bonds. And so let's highlight that, and then we'll bring it back to what you said about catabolic and anabolic processes. And so we can say, and right, they're kind of telling us, so what we're looking at, so breaking bonds right? That requires energy. So it says the cost of breaking bonds. So that's considered an endothermic process. So we have to add energy. And so, right, we can kind of, so then we'll compare. So then, and then making bonds. So making bonds gives us back energy. So that's thermodynamically favorable. So that's going to be exothermic. And so you can kind of relate it to catabolic and anabolic processes. And so this is kind of an aside, right? But so we were saying, so catabolism or catabolic and so catabolic, it's the overall process. So we said that it broke down molecules. And so this is kind of now the more overall process. So this is breaking down molecules. And so we see that this breaks down molecules and releases energy. So this would be exothermic. And supplies energy to the cells. And so, right, we can see how you're breaking down molecules, so getting the energy from the bonds, kind of versus an anabolic process where you're building molecules and all that would require energy. I'm not sure that was that related. I don't know if that was confusing or.
But right here it says breaking bonds is endothermic, which means it takes energy.
I know,
So
that's what I'm
breaking
kind of.
molecules.
It's because it's like the overall catalytic pathway. So now I'm thinking that maybe that was more confusing. But because you're catabolic, right, you're taking one big molecule, but it's still the same process though, right? Because you're breaking down energy, and so you're breaking those bonds, and then you're using the bond energy for your cells. And so they are related. Versus, right, the anabolic process, so you're overall building a molecule and then putting energy into that. But I think that came out more confusing. All right. We'll revisit this later if we need to. And so looking at this, so other requirements and kind of just the standard state, so kind of the standard bond breaking, bond making is in the gas state, and then we have this homolytic concept, and so that's just homolytic cleavage, where each atom gets half of the bond, and we should define homolytic versus heterolytic. So homolytic would just be like your standard methane. So let's just say, and so then we use this little half arrow to show that there's 2 electrons, right? And then 1 is going to each one. So this would be a homolytic cleavage. So showing that. And so versus, we don't tend to see heterolytic cleavages a lot, but let's just look at an example. So a heterolytic cleavage would be like BF3 and some sort of nitrogen compound. So we could do ammonia and BF3. And so with this, if we were to draw out the Lewis dot structure, right, our nitrogen is donating 2 electrons. And so then when this cleaves, it would be heterolytic because the 2 electrons from that bond go back to the nitrogen instead of course, right, doing 1 to boron, 1 to nitrogen.
Okay, so you're saying like when the bond is broken, the electrons would usually in a homolytic, they
Yeah, and that usually goes back to like where the electrons came from originally. And so homolytic, you can also call them like normal bonds. So like most of the time, each atom is donating 1 electron to every bond. So that's,
So would that also be like in making ions? It would be heterolytic?
oh,
So like if hydrochloric acid broke apart into hydrogen and chlorine, chlorine would just take it and then the hydrogen would just be a proton?
Well, that's not a
yes,
chemical bond, though.
yeah,
It's an ionic bond, so you would just be pulling it apart.
exactly. So did his comment make sense? Because that's the difference. Because here we're actually breaking, right, a bond. So there's actually a covalent bond. But what you're talking about is just more like charge separation. Because right, they have no bond to begin with. They're just held together by the electrostatic forces.
Okay.
But this is more measuring, right, the energy within that bond. So it's little different formality. Because with the ionic, you have to take into account the whole crystal lattice structure, so that's what gives it energy, versus this, where we're just looking at one bond, and again, looking at that normal cleavage, we'll say. All right, so starting to run out of time here. So we'll leave off with this. So we have our bond energies, and we'll see what we'll pick up on Thursday. So we have this table of bond energies, and then so we'll kind of see how we can quantify that. So we're going to look into breaking bonds. So again, at least appreciate that's going to be an endothermic process, and then we'll make the bonds. That's exothermic, and then we'll compare. But we'll save the math for Thursday, so that's where we're going. And then make sure you get papers from me. I have a lot of papers. I have a ton of papers for you.
I think, yeah,
Actual minus
So, see, this is where you went wrong. From the one plan.
and then what?
Yeah. Yeah,
how I am about that.
Yeah, I'm not very worried about it. The other thing that I think that mostly I keep having dreams that I'm just falling apart. I'm like, no.
Oh, I've had my fair share of nightmares about traveling.
Yeah.
Oh.
For me, the dreams always include my younger brother and my dog, like being passengers
Oh
on the
no,
car.
that's even worse.
And that's what makes me
For
I
you.
wake up and I'm like,
And then you said, oh, I'm gonna stop the stream.
I need to